Harley. It will take some time. I got a very long list of bullet points. Yeah, okay, so welcome everyone. Next ITC Colloquium, and we're honored to have Harley Katz. So Harley did his PhD at Cambridge with JWST. So he has he's like a descendant of the ITC family in the sense. After that, he joined Oxford as a Beecroft postdoctoral fellow for 1 year, and then he changed the direction from contributing to humanities knowledge of astrophysics, going to industry and affecting people's lives in more direct ways. So he was the co-founder of Probability Genetic, a genetic startup working on rare disease diagnostics. And then, after a few years, he moved back to astrophysics. He moved back to Oxford, and then in 2024, he joined the University of Chicago as a faculty member. And today, Harley will tell us about spectral resolution and cosmic dawn.
Awesome. Thanks, Vadim. It's great to see many of you. It's my first time here at Harvard, and so for those of you I haven't met, it's great to put a face to some of the names I see on papers. I'm primarily a theorist, as you could have probably guessed from me being Deborah's PhD student. But over the past couple of years, I've sort of taken a brief hiatus into the observations while one of my simulations was running. That simulation, as of 2 days ago, after 2 years on the computer, is finally done. So I can give up observations and go back to my theoretical roots. So I'll talk a little bit about both theory and observation in this talk. So you can't really talk about High-Redshift without showing a slide like this. Briefly, it's the history of the universe on a single slide. You have the formation of the CMB here about 400,000 years after the Big Bang. As the universe was expanding, it started cooling down. Eventually, by about 1 to 200 million years after the Big Bang, gravity really started taking over, and you had the formation of the first metal-free, as we call them, population 3 stars. Okay? And so these population 3 stars, we think, were probably slightly more massive than what we have for population 2. They emitted lots of ionizing photons. They were very hot. But most importantly, they ejected metals into the universe. That spawned the era of population 2 star formation. Galaxies started forming. The reionization bubbles started growing. And by about a redshift of 5.3 or so is the number now, the universe was fully reionized. Okay? And prior to James Webb, we had Hubble, which was really a fantastic instrument, and Hubble pushed us back to about a redshift of 11 or so. That was roughly the highest spectroscopically confirmed galaxy with Hubble. Now, the promise of James Webb was, if we're lucky, we might even be able to push back to the formation of these first population 3 stars, which would be what we describe as cosmic dawn. And so why can James Webb do this? For one, it has a much bigger mirror. This is just a scale comparison of James Webb compared to Hubble. We weren't satisfied with silver. We painted this one gold. We cooled it down to a much lower temperature. It allows us to see infrared photons. We can push back even further in redshift. And so the state of affairs with the Hubble Space Telescope, on the x-axis here you have redshift. Y-axis is the UV luminosity density, which is a proxy for star formation rate. You can see that with Hubble, we pushed around to about redshift 10. And of course, with James Webb coming online, this is already outdated. We're about to a redshift of 14 or so. Okay? And so for those of you that don't study the high redshift universe, 10 to 14, that's not super impressive, is it? What's a couple redshifts between friends? But if you think about it, at redshift 14, the universe was 2% of its current age, and I think that is really quite remarkable. We're almost there. We're almost really at the cosmic dawn. But then also, time's going pretty fast at these epochs. Redshift is, kind of misleading sometimes. And between redshift 14 and redshift 10, the age of the universe increased by 50%. And so there's really quite significant evolution that can happen between redshift 10 and 14. So really, this is opening up a brand new era for us to study. So just to compare a little bit between Hubble and Webb, this is GNZ11, which is the highest spectroscopically confirmed redshift galaxy with Hubble. And you can see, we had a redshift for it, but pretty much it's this, red blob, right? There's not much we can do with just this image. And then you can do the same thing with the James Webb Space Telescope. Slightly higher resolution, but it's still pretty much a red blob. Like it's definitely more impressive, but it's still very much blob-like. Okay. Nevertheless, there really has been a revolution in the imaging. Really, it comes from being able to go deeper and to longer wavelengths. And I think the sort of first really big result from the imaging side of things was that there may be what we call an overabundance of bright galaxies at high redshift. So if you look at redshifts on the x-axis, and this is just the surface density of sources with a apparent magnitude less than 28.5, this sort of gray region is the estimates from the Sears survey, and all of these different colored lines are these different models. And the vast majority of these models are falling well below what we get from the Sears data. And so there may be some tension with some of these observations in the models. I should put a caveat here saying, there's many simulations pre-James Webb that actually did get this right. Here's just 3 of them listed down here. Nevertheless, all models are, of course, not in good agreement. But the imaging side has been really instrumental in pushing us to these extremely high redshifts. However, I am most interested in spectroscopy, and here you're going to see a major difference. Okay, so here is the Hubble GRISM spectra of GNZ11, and you can see that there's barely any flux here, and they estimated a redshift of around 11.1. So this is this red blob galaxy. If you look at the exact same spectra with the James Webb Space Telescope, you see a remarkable difference, right? What we barely got a redshift for now has all these absolutely beautiful emission lines. You have a full continuum detection all the way through to some of the emission lines in the rest frame optical. And this is really where I think the physics is going to be fantastic over the next 5, 10, and hopefully even longer number of years. And so as a theorist, extracting the physics from these spectra, I'd argue, is actually a key theoretical challenge. And so this is an example of one of the first high redshift spectra taken with James Webb. It's from NIRSpec. It's a galaxy at redshift 8.5. Again, you see these beautiful emission lines. If you look at something like H-beta, that's telling you some information about the star formation rate. If you compare to Balmer lines where we think we know the intrinsic ratio, that tells you about the dust content of the galaxy. If you compare different ionization states, for example, oxygen 3 to oxygen 2, that could tell you something about the ionization parameter in the interstellar medium. You can compare oxygen lines to Balmer lines. That can give you some insight into the metallicity of the object. And of course, if you look at the shape of the continuum more generally and sort of its amplitude, you can learn about the star formation history and stellar mass of the object. Of course, this is all an emission. You don't actually have to do that. You can also look in absorption. So here on the right, you're seeing a mu spectra of a galaxy at redshift 1.3, these beautiful absorption lines. This is telling us about the gas sort of in and around the galaxy, so more towards the circumgalactic medium. You can learn things about the metallicity of an outflow, outflow velocities, column densities in the circumgalactic medium, and total mass outflow rates. And so, over the next 5 to 10 years or so, we're really going to get a detailed look at the ISM properties up to about redshifts greater than 10, and CGM and outflow properties probably somewhere greater than redshift 5 or so. And so having done this now for a couple years, it's been really exciting because just like there were these anomalies I told you about in the imaging, there's also anomalies in the spectra. We're finding some real weird physics at high redshifts, okay? So here's one of these first examples. This is metallicity on the x-axis versus nitrogen to oxygen on the y-axis. This is a compilation of low redshift data, so you see there's sort of a plateau here, and then it sort of increases towards higher metallicity. But if you look at GNZ11, this is some work we did with Alex Cameron a few years ago, you can see that it's rapidly enhanced in nitrogen in context with all of the local systems by very significant amounts, okay? What's also interesting is this is some work by Yanagisawa et al. If you look at nitrogen to oxygen on the x-axis and versus helium over hydrogen, there seems to be a very strong correlation between galaxies that are enhanced in nitrogen are also enhanced in helium. And that's not surprising. That's expected from stellar evolution and enrichment patterns. But this does have significant effects on the galaxy, and I'll show you how. If you remember your STARS class in all of your graduate programs, if you put the helium mass fraction on the x-axis and the bolometric luminosity of the stars on the y-axis, there's an increase such that at higher helium abundances, you find that stars are much more luminous, okay? And if I put 2 of the nitrogen emitters at high redshift, GNZ11 and GHZ2, you can see that the stars in these galaxies are expected to be 50% brighter, doing nothing about star formation, nothing about the IMF, just enrich them a little bit in helium, and your stars are brighter. And that's probably, it's a very trivial result, but hasn't really been considered in the context of these high redshift galaxies. Another interesting thing is that the nebular continuum in many of these high redshift galaxies is exceptionally strong. So for those of you that don't work on nebular continuum, this is emission that's coming from the gas. And so here's just a stack of galaxies I made. It's about 60 in the stack. And what you'll notice is that there seems to be a jump feature here. So on the right-hand side, or redward, you see the continuum is lower, and on the left-hand side, the continuum is higher. And this is what's called the Balmer jump. It's a free-bound recombination feature, and we know that this is a gas emission feature. And we've seen this at low redshift. In fact, the physics of this is extremely well understood. Here you're just looking at some results from simulations. There's 3 different star formation histories. There's just a smooth star formation history, kind of a cyclic but bursty star formation history, and then a galaxy that's undergone an extreme recent burst. The cyan line is the stellar continuum, and the magenta line, this is the nebular continuum. And what you can see is as you go from a smooth star formation history to a bursty star formation history, the nebular continuum is popping up, and you can see that as you go to the burstiest modes of star formation, the nebular continuum pops up above the stellar continuum, and you see this Balmer jump. So again, all the fact that you see this Balmer jump is indicative of bursty star formation histories. Again, that's not super surprising. But what is surprising is that for some of these galaxies, the nebular continuum is not just outshining around the Balmer jump, it seems to be outshining the stellar continuum over almost the entire spectral coverage of this galaxy. And the reason why we know this is because here you see a beautiful Balmer jump. These are just 3 examples where you can see it's lower on the right-hand side than the left. You see a very flat UV slope. And you also see a downturn here, which is due to 2 photon emission from hydrogen going from the 2s to 1s state. I'm going to describe this a lot over lunch in 10 minutes, so I'm going through it relatively quickly. But we're convinced that these are very, very exceptionally strong nebular continuum because the Balmer decrement shows us that there's almost no dust in these galaxies. And if we're correct, what this implies is that some of these high redshift galaxies are hosting some sort of hot mass of stars that may have a top-heavy initial mass function. Another thing that I've been really interested in recently is the idea that many of these galaxies at high redshift, particularly this little red dot population, are showing evidence for Balmer breaks that may not be stellar in origin. Okay? And so for those of you that aren't familiar with Balmer breaks, typically this is a feature that pops up in sort of slightly older, lower mass stars, where you see a downturn here going from red to blue. Okay? And it's something that happens in the stellar atmospheres of these stars. Now, what's really interesting is these 2 objects. So the top one was published recently by Rohan Naidu, and the bottom one is from the Ruby survey from Anna de Graaf. And what you can see is that there's actually an absolutely huge difference between the right-hand side here, the red, and the left-hand side blue. So if you just focus down here on the bottom, you see this sort of like massive upturn here. And if you just compare to sort of other little red dots in the literature, you see that this one is just an extreme outlier. And if I put these, what I call Balmer breaks, in the context of other sources, so here's our 2 objects here. This break strength is just quantifying sort of the difference of the continuum up here to down here. You see this is around sort of 6 to 8. High redshift galaxies are typically, around 0.5 to 1. Sometimes they have a jump rather than a break, which means this can even go negative. Massive quiescent galaxies, which are known for their Balmer breaks, are sitting around 2 to 3. And some of the other little red dots in the literature are sort of well below. And in fact, we couldn't find an individual star that gave us a break as strong as this, which got us to thinking, is there a way to create Balmer breaks without using something like a stellar atmosphere? And the answer is categorically yes. These are very simple toy models using Cloudy, where we essentially set up what we're calling like a gaseous atmosphere that's sitting around a relatively modest mass black hole. Here's the parameters, and we can get break strengths that are pretty much in agreement with what we see. And we can also get H beta in emission and H gamma in absorption, which is what's seen in the high resolution spectra. And so what it seems to be is, at least for some of these little red dots, there seems to be these black holes with almost like stellar-like atmospheres sitting around them. Okay, so these are some of the weirdos at high redshift. But I think, coming back to the normal galaxy population, we're now sort of in this very fortunate position where we have thousands of spectra. Okay, so we're in a position where we can explore the populations of these galaxies at high redshift in the way we were starting to do at low redshift with Sloan. So here's just 2 examples from some work by Alex Cameron and Ryan Sanders. The classic R23032 diagrams and the N2BPT diagrams. You can see the high redshift galaxies are sitting well above what we see at low redshift from Sloan, both here on the R23 and then again here in the O32. And again, interpreting the ISM physics that's leading to these differences at high redshift compared to low redshift is what we'd like to understand as theorists. And so you can ask, how do we interpret these diagrams? So traditionally, what we do is we use what's called photoionization models. And so the idea behind this is extremely simple. You put some sort of ionizing source inside of some, in this case, it's a spherical shell of gas. You can use a sphere, you can use a slab. It's not super important. You can vary things like the metallicity, the ionization parameter, the density, the spectral shape, et cetera. You just evolve that thing until it reaches equilibrium, and you calculate the type of emission that's coming out of it. And this has been done for years and years and years. This is an example from Lisa Cooley's very classic 2001 paper of the N2PPT diagram, where you see they ran a grid of photoionization models that perfectly can map out the sequence, and you can see it's dependent on both ionization parameter and metallicity. And this has been the absolute workhorse of this space for a very long time. Of course, these are extremely simple, right? And if you look at a real galaxy, it does not look like a photoionization model, right? You have a lot of other physics that's going on. Galaxy formation physics in general. You have shocks, you have turbulence, you have all these sorts of things that make up this galaxy. And so I think the real open question now that we've spent $10 billion on a new telescope is, where can these photoionization models go wrong, and how can we actually improve them? I'm going to give you 3 examples of where things can go wrong. The first one is very simple. The presence of turbulence modifies emission line diagnostics, okay? So here's a very simple example where all we've done is we've taken a homogeneous medium, we've put a source in the center of that medium, and we've evolved it to equilibrium and calculated the emission lines that are coming out of it. Then we take that same medium, we stir it with a little bit of turbulence, we freeze it at 10 different epochs after it's turned over a few times. We put a source in the center, and then again evolve it to equilibrium. So here you can see a stirred up medium. This is just the 3D gas density, column density, the temperature map. So now you don't have a spherical H2 region, you got some weird butterfly structure. You can see the oxygen 2 is forming right at the edge of the Strömgen sphere, and the oxygen 3 is this volume filling medium. And so what you can do is you can look at our standard diagnostics, O3 over H beta, N2 over H alpha, or O32, as a function of metallicity. The black star is what you'd get from running something like cloudier mappings or R code in the homogeneous case. And you see you get some evolution with metallicity. But if all you do is change the geometry, okay, run it 10 different times, you now no longer have a single value. You have some median with some scatter. And you can see that O3 over H beta systematically decreases, N2 over H alpha systematically increases, and O32 systematically decreases. So all we've done is change the geometry, and our interpretation of the ISM at high redshift has changed, okay? This result is not unique to us. If you know Yifei Jin, he's probably here somewhere. He found the exact same thing with his code. Again, O3 goes down, and then these boundary species like the oxygen 2s, those tend to increase. And so this is a very important effect we need to quantify, especially at high redshift where we know the gas is turbulent. Another impact is non-equilibrium effects. So these we think are very important in the CGM, but they do sometimes matter in the interstellar medium as well. This is a result from one of our simulations. On the x-axis is density, on the y-axis is temperature. And the color shows you the ratio of the electron fraction in non-equilibrium to the electron fraction in equilibrium. And so everywhere you see green, this is gas that's being over-ionized. This is an extremely well-known effect. What this is basically the gas can cool faster than it can recombine. This is a recombination lag, which leads to over-ionized gas at a given temperature. Okay? And if you change the electron fraction, you change your collisional partners, you change your emission lines. There's another effect here which is rarely discussed. This is under-ionized gas, so the gas has a lower electron fraction than you'd expect for its temperature. This is a little bit rarer than the recombination lags, and in our case, this is a cosmic ray effect that I can go into if you're interested in. Okay, a third place photoionization models can fail is it turns out that the distribution function of H2 region properties can bias our measurements of certain physical properties of galaxies. Again, this is a very simple toy model. Imagine you have a cloud that has some metallicity but a uniform temperature, okay? You can then try to estimate the metallicity. In this case, we're using what's called the direct method, which is, I'll go into it in a bit, but it's considered to be the gold standard of metallicity estimates at high redshift. So if you just vary the mean temperature of this cloud and measure the deviation from the true metallicity based on this direct method, you find that when you have a homogeneous temperature cloud, you can perfectly recover metallicity. And so that's fantastic. But if you again, fix the metallicity, but allow for some sort of temperature fluctuations in the cloud, depending on whether or not the temperature fluctuations are Gaussian distributed in blue or log normal distributed in orange, if you change the mean temperature, again, what you find is that you always systematically underpredict the metallicity if there's temperature fluctuations present in your medium. And this is a strong bias that we know has to exist in our real universe. The question is how large is it? Okay, so you can ask the question, we know photoionization models fail in certain regimes. How can we improve on this? And I think one of the obvious things to do is you can try to combine these photoionization models with galaxy formation simulations. And so we've been doing this for many, many years. This is an example of a simulation we ran, I think, in 2017. You have a beautiful disk galaxy at redshift 10. We put it through some combination of photoionization modeling, which I'm just going to call the black box of post-processing. And if you spend enough CPU time on it, what you do is you can pretty much model any emission or absorption line feature out there. Here's just a few examples of predicting infrared lines in the context of ALMA. But I want to highlight the important thing here is that there's a huge amount of assumptions in this black box of post-processing. I've listed some of them down here. It's so bad that people have post-processed the same simulation and gotten orders of magnitude different emission line luminosities. So the predictive power of this method is not that strong. And I'm saying that as someone who spent many years of my career actually working on this. Nevertheless, you can still learn a lot about this. So here's some results from our Sphinx simulations where we've done this type of post-processing. Here's some beautiful cutout images here. We now have a public library of more than 14,000 mock images in Spectra that have been fully processed with resonant line radiative transfer, dust radiative transfer. So you can see an example Spectra here in black. And if you process it through dust, view it down 10 different lines of sights, you can get very different answers for what the observed spectra is going to look like. Now, having libraries this large is, I think, extremely useful. This is a really fun project we did with one of my graduate students based at Oxford. And by having spectral libraries this large, you can actually bypass traditional SED fitting techniques. So what my student Nick did is he mocked the photometry of every single one of our galaxies in this 14,000 spectral library. And what he tried to do is he tried to predict the number of ionizing photons that are actually escaping the galaxy into the intergalactic medium, which is an interesting quantity in the context of reionization. He did this using an implicit likelihood inference, which is a machine learning technique. On the left-hand side, you're just seeing the true value of n dot ion and the predicted value on the y-axis for various redshifts that we did this exercise for. You can try the same exercise using traditional SED fitting. In this case, he used bagpipes using two different models for how the escape fraction should change with observable properties. And what you can see is, of course, on the left-hand side, the model was trained on this to do really well. On the right-hand side, you see there's strong systematic biases when you use this traditional SED fitting codes to predict the number of escaping ionizing photons. But of course, because this was trained on the photometry and not the spectra, you can apply this to all 40 or 50,000 JADES galaxies that are now in the public database, and you can actually predict the number of leaking photons as a function of redshift. And this is what Nick did, and you see there seems to be this smooth trend moving from low to high redshift, where the galaxies are leaking essentially F escape times the ionizing photon production efficiency tends to be increasing. Okay, and so this technique of combining photoionization models with simulations, I think, has led to a lot of advances in our understanding of the observations, but I've decided about 4 years ago it's time to do a little bit better. And so how do we do that? The idea is to take all of this detailed physics that's in these photoionization models. So these are all of these processes that control the ion and molecular properties of the gas. So for example, collisional photocosmic ray ionization, various recombination processes, charge exchange processes, and we're going to try to put those and solve for them directly in our 3D galaxy formation code. And so here's just a very simple toy model. On the x-axis is time in megayear. On the y-axis is the ionization fraction. We started it in completely neutral, and what you do is you evolve it in time until it reaches equilibrium. The dotted lines are what you expect from the photoionization models. For example, in this case, it's cloudy. So that's what you get in equilibrium. But of course, our code runs fully in non-equilibrium. So depending on whether the system is in or out of equilibrium, we can find ionization fractions anywhere along these curves. Of course, just getting the ion and molecular properties isn't everything you need. You also need all of the processes that control gas temperature. So these are things like heating from cosmic rays, photoelectric heating, H2 heating, various cooling processes, and of course, the processes that heat or cool a gas due to galaxy formation, adiabatic expansion, supernova, turbulence, shocks, gravitational compression, et cetera. And these are sort of all, again, calibrated to try to match what we can do in the photoionization models, but then be run in a galaxy formation setting in 3D. And of course, we have to calibrate this on something. What we do is we calibrate it on the local Milky Way ISM. So here you're looking at density on the x-axis in both plots, and then temperature or pressure on the y-axis. The green line is the solar metallicity curve, and it's calibrated to basically go through these orange points over here, and it has this S-curve here, which is indicative of this ISM being multi-phase. Of course, it's calibrated at metallicity of 1, but we can run it at any metallicity we want, and that's given by these different colored lines. So as you see that if you decrease the metallicity to 10% solar, the cooling instability actually happens at lower density, and I can discuss the physics if you're interested. And then if you decrease it further, you see your ISM actually turns from what was a multi-phase medium to a non-multi-phase medium at the lowest metallicities. Okay? And you can ask, why haven't people done this before? And some people have, but the major difference between our code and these other codes is we had to develop a specialized ODE solver to get this to actually work and run for a realistic simulation. And we've benchmarked it against some of the more commonly used ones in the literature, and ours is over an order of magnitude faster, which has just opened up a new class of problems that we can study. And again, for those of you that are aficionados of the photoionization models, our results can be run in a photoionization model setting. We can just set up, again, a homogeneous medium, put a source in it, and evolve it to equilibrium. On the x-axis is density, on the y-axis is luminosity of various different strong emission lines that we're used to seeing. Cloudy is given by the solid lines, and our code is given by the data points. And you can see that over a very wide range in density, our models are almost in complete agreement. The differences are fewer than 10% between us and Cloudy. There's some differences in atomic data choices. There's some differences in dust depletion rates. So we don't expect exact one-to-one match, but 10% is the difference between Cloudy and mappings on average. So we're right in the ballpark of that as well. For those of you that don't do this, just to try to put this a little bit into perspective, so while most simulations predict what I would consider to be the intrinsic properties of galaxies, so these are things like their gas density distribution, the stellar distribution, the gas temperature, when you run this Ramsey's RTZ and PRISM model, you can actually directly predict the observable. So of course we get all the ionization states of hydrogen and helium, we get the temperature map, we get molecular hydrogen, carbon monoxide. Here I'm just showing you 4 radiation fields from the far UV to the helium-2 ionizing. But if you look right here on the right, this is not post-process. We predict the emission line luminosities if you know H alpha to any line you want down to nitrogen 2 here. And that's, I think, really fantastic. There's no more post-processing. Everything is done on the fly, fully in non-equilibrium. And so you can ask, what can you do with this? Here's just an example of a very simple isolated galaxy simulation. It's roughly the mass of the SMC. Here, again, you're seeing maps of H beta, oxygen 2, oxygen 3, 5007, and 4363. You can see how these emission line luminosities are changing as a function of time. This is sort of responding to the star formation rate in the simulation. And you can ask a very simple question. How well can we extract the underlying physical properties of this galaxy using standard observational techniques? So I'm going to go through one example, and that's metallicity. In principle, metallicity is extremely easy to calculate. Okay? So imagine you have sort of some unit volume which has some temperature and some density of oxygen 2, oxygen 3, ionized hydrogen, and some temperature. Okay? The luminosity coming out of this unit volume of gas just goes as the emissivity of the line, which is something that we estimate from quantum mechanical calculations. That's a function of temperature, and then you just multiply that by the number density of electrons and then the number density of the species. And you can do the same thing for oxygen 2, and you can do the same thing for H beta. So of course, we know the number densities. We've set this problem up. We know how the emissivity scales with temperature, so all we need is the temperature. Okay? And it turns out you can estimate the temperature by taking the ratio of what's called the oxygen 3 4360 line, 4363 line to 5007. And again, this is very well-known physics. And so once you have the temperature, you have these luminosities. Then the metallicity is just the number density of oxygen to the number density of hydrogen, which just goes as the singly ionized hydrogen plus doubly ionized hydrogen over singly ionized hydrogen. Okay. This is a pretty good approximation. These ionization states are extremely well coupled via charge exchange reactions, and we don't expect too much O4. If you just sort of work these things out with respect to the luminosities, it's just a ratio of luminosities times ratios of emissivities. So you measure your luminosity, you estimate your temperature, and you get your emissivity. So you pretty much have everything you need. So what I did is I gave my simulation to our resident observer, Alex Cameron, and I said, why don't you tell me what the metallicity of our galaxy is? On the on the x-axis is the true metallicity. On the y-axis is what Alex predicted using what's called the direct method, which again is the gold standard at high redshift. The dashed red line is the one-to-one relation, and what you can see is that all of his estimates are systematically below the one-to-one line. This is again due to temperature fluctuations, but really what it comes down to is that the temperature that we measure from 4363 over 5007 is not the temperature we need to use the direct method. So on the x-axis is this 4363 to 5007 temperature. This is what we can actually measure from observations. And on the y-axis is what we call the line temperature. And this is the temperature that one actually needs in order to calculate the metallicity correct when there's temperature fluctuations present. And you can see that 5007, O2, and H beta, the line temperature is always systematically below the ratio temperature. And so what you can do is you can do the dumbest thing. You can just say, OK, there looks to be some relation between the line temperature and the ratio temperature. I'm just going to fit that relation. And I'm going to see how the mass metallicity relation changes if I sort of measure my T ratio and convert it to a T line and use that to solve for metallicity. And so here is the mass metallicity relation. On the x-axis is stellar metallicity, on the is stellar mass, and on the y-axis is gas phase metallicity. This black line is what's in the literature. Okay, this is the mass metallicity relation using the standard direct method, the gold standard again. And if we recalibrate that using our relation between T ratio and T line, you see that there's a systematic shift upward. Okay, and so not only does the shape change, but it also changes in normalization. And of course, this is a constraint on a lot of our galaxy formation simulations, and it's objectively wrong. Now, one thing to keep in mind is our simulation is a single object, so this relation between T ratio and T line is by no means the end of the story. But all I'm saying here is that if you take some reasonable relation between the two, you're almost certainly going to get an increase in normalization and a change of shape. The exact magnitude, I think, is still under debate, and we have to do a lot more to actually constrain what it is, but it will change and it will come up. OK. So these were toy models, but now over the last few years, we've been running a new simulation, which we call Megatron. And what it is it's an early forming Milky Way mass galaxy. So it turns into Milky Way mass at around redshift 2 or so. It's got pretty high resolution. It's got around 1 parsec resolution when the first stars form. We model both population 2 and population 3 stars. The IMF is fully sampled. We enrich elements individually. It's got various forms of stellar feedback that have all been calibrated at redshift 0 using the Wintergatan suite from Oscar Agertz, if you're familiar with that. We use an 82 species chemistry model coupled to 8 bins of radiation transfer. Another thing we do, which is quite fun, which I'll show you later, we enhance the resolution in the circumgalactic medium. We're an AMR code, so what we can do is we can refine wherever we want. So in this case, we're refining on the cooling length. And then we have various physical models using stronger feedback, weaker feedback, variable IMF, et cetera. There's sort of 4 key scientific goals of this. It's sort of star formation at cosmic dawn. How do the first POP3 stars form and metal enrich our universe? What do galaxies look like in the epoch of reionization? What can the emission line diagnostics tell us? And can we recalibrate them and apply that to James Webb data? What can we learn about the CGM towards cosmic noon? Is the CGM in equilibrium? Is it out of equilibrium? Can we learn about metal and mass outflow rates using, again, these absorption line studies? And of course, because it's a Milky Way mass galaxy, we've run the dark matter to redshift 0, so there's going to be a connection that we're working on between high redshift galaxy formation and low redshift. So here's just a video of what the galaxy looks like between around redshift 5 and 4. You're looking at dark matter on the top left, the gas distribution, the stars, the gas temperature, the Lyman-Warner flux, and the ionizing flux. And you see as the star formation rate is going up and down, the ionizing flux is pulsing. Most of the time it doesn't get out of the galaxy. Occasionally it does, and it ionizes their circumgalactic medium. The galaxy is much more optically thin to the Lyman-Warner radiation, so you can see that sort of spreads out almost as 1 over r squared. Okay, and you've all seen videos like this. You've probably all made videos like this. What you probably haven't seen before, though, is because we're solving for the ionization states of all of these metals in and out of equilibrium, we actually, again, predict the emission line fluxes as a function of time. So here's videos of what those look like. You can see that the H alpha is fluorescing in emission as the ionizing flux is penetrating out of the galaxy. You can see the same thing is happening to oxygen 3 as the star formation rate is going up and down. You see in particular the CGM is changing its ionization state on very, very rapid timescales. And this is sort of the unique selling point of these simulations is that, again, we can predict these things from first principles. If we move to higher redshift, here you're seeing the simulation from redshift around 20 to redshift 10. You see these white bubbles forming. This is H beta in emission. Ionizing radiation is leaking out of the galaxy. It's ionizing the intergalactic medium, and some of that is recombining to give you this H beta emission. In the meantime, as the population 3 stars explode, metals are produced. This is this yellow emission is oxygen 3 5007 emission from the gas. You see the metals are now permeating into the intergalactic medium. They're changing their ionization state, so these yellow bubbles fade faster than some of the white ones. And of course, that leads to population 2 star formation. Gas cooling times are much shorter. Star formation is more efficient, which can lead to these sustained oxygen 3 galaxies. And so by around redshift 9 or 10 or so, you see the metals have really penetrated now far away from the galaxies. The volume is becoming reionized. You see the filaments, again, are fluorescing, and the movie stops around here. Okay? And what's nice is we can pretty much now use these simulations to mock any of the observing modes with James Webb. So here's just a galaxy at around redshift 4. We've sort of laid a slit over it. This is what it would look like in the near-spec MSA. I haven't convolved it with noise, of course, because that would make this look a lot worse than it does. There's a mock IFU. Here you can see H alpha. This is the receding side and approaching side have very different morphology. And of course, the underlying near-cam images just combining into an RGB. We can't do the GRISM yet, but we can pretty much do any of the other observing modes with near-cam and near-spec. And so what's nice about these simulations is without post-processing, for free, we have more than 200,000 spectra across the entire Megatron suite of simulations. And what I'm extremely excited about is that we can reproduce the full spectral diversity seen with James Webb. So in this experiment, what I've done is I've taken 200,000 spectra. So they have roughly 1 angstrom resolution. So this is, of course, not what we have with near spec, but it's what we compute with our simulations, and we can downgrade it to any resolution that we want. And we just throw it at UMAP, and all UMAP does is it just takes your very high dimensional space and tries to project that into lower dimensions, okay? And so there's just a UMAP parameter 1 on the x-axis and UMAP parameter 2 on the y-axis, and anything that's sort of close in this embedding in low dimensions is also closer in higher dimensions. And what you see is that there seems to be some sort of like continuum shape here on the left, and then an offset region here on the right. And I've just, by eye, sort of cut these things into clusters, and then I've stacked the spectra inside these individual colored regions. So if we start at the bottom right in this sort of panel, and you stack the spectra, what you see is these star-bursting galaxies. You see this booming Balmer jump, extremely high equivalent width emission lines. As you move to sort of this, I don't even know what color that is, sort of pinkish cluster, you can see the Balmer jump has weakened. The emission line luminosities have come down in terms of their equivalent widths, and these are what we call their star-forming galaxies. Continuing up this trend, now you move into what I call aging and post-starburst galaxies. You now see a Balmer break starting to form. And moving all the way into this top right, you see this mini-quench galaxies. I guess Tobias isn't here, but I imagine he would be excited to see that. And finally, there's one more set of galaxies here on the right. This is this blue region. And what those are is these are our population 3 galaxies. And the reason we can tell is, again, there's a booming Balmer jump. There's clear 2-photon emission. And if you have a keen eye, you can see the booming helium-2 1640 line right there, and a slightly fainter one there in the optical. So one of the things I think is really exciting about these high redshift observations is I think that the interstellar medium holds enormous potential for constraining galaxy formation models. And so here's actually results coming from our calibration simulations, not even the full suite. So here you're just looking at, on the x-axis is the age of the universe, and on the y-axis is the amount of stars formed. And these models are identical. The feedback is the same. The resolution is the same. The only thing we've done is we've changed the minor differences in how we form stars. So in these cases, they're all density-based models, but here they have different efficiencies of 100% and different density thresholds. And you can see that by redshift 6 or so, they form very comparable numbers of stars. But if you look at the interstellar medium for these galaxies, here you're looking at a probability distribution function of oxygen 3, 2. you can see that if I just make very minor changes into the efficiency of star formation and the density of star formation, you see that the histograms start changing. So in this case, when I increase the density, your oxygen 3:2 ratio goes way up significantly compared to the density model. So for all intents and purposes, our luminosity function is the same, our stellar mass function is the same, our stellar mass to halo mass relation is the same. But the ISM is telling us a lot about what is going on in the interstellar medium. And now that, of course, we have these at high redshift with James Webb, here's a purple histogram from the JWST primal survey. You can actually use this now to constrain these star formation models in ways we couldn't do before. Coming to the full suite, I'm just going to highlight a few very quick results. One of the things that we're excited by is that if you look at the star formation rate of population 2 stars, which are the solid lines, and population 3 stars, which are the dashed lines, you can of course see at very high redshift, towards redshift 30, everything starts with population 3 star formation, but that quickly gets overtaken by population 2 stars. So perhaps it's not surprising that with James Webb we haven't directly observed population 3 stars, because the star formation rate is completely dominated by population 2 stars after the first burst of population 3 star formation. However, what you see is that a huge fraction of this Lagrange volume around our Milky Way galaxy is staying metal poor, such that even by redshift 8.5, we're still getting a small amount of population 3 star formation. So, what Fengwu was talking about yesterday, and Rohan was talking about yesterday, seems to hold in our simulations as well, where we can get this late population 3 star mode, which is interesting in the context of direct detection. One of the things I think that surprises a lot of people, though, is that the way people are looking to detect population 3 stars is kind of different from what our simulations predict. So on the x-axis, you're looking at redshift, and on the y-axis is UV slope. Most people are constraining their surveys to look for these very blue galaxies to try to find population 3 stars, so beta's around -3. But if you actually look, our population 3 galaxies all have UV slopes between -2 and -1.5. So our population 3 galaxies are significantly redder than what we find for our population 2 systems. However, robustly detecting population 3 is going to be extremely difficult, because on the x-axis is metallicity, on the y-axis is the O3 to H beta ratio. You can see at metallicities of 10 to the -2, the oxygen 3 line can be around sort of 10% or less of the H beta line, which is going to be very hard to detect. So it's going to be very difficult to know whether a galaxy is just very metal poor or lacks metals completely. Another thing that was a little bit surprising to us is that all of our models, varying the different feedback physics, predict that at high redshift, so in this case redshifts greater than 15, we have galaxies with MUV brighter than -17. So here are some photometrically selected high redshift galaxies from the GLIMP survey, and every single one of our models, independent of feedback, is predicting that these very high redshift galaxies can occasionally get this extremely bright, and I think that's very optimistic now for the detection of galaxies up to about redshift 20 or so using gravitationally lensed surveys. One of the things our model, I think, does really well is it predicts a variety of extreme emission line galaxies. And so these are galaxies that have H-alpha equivalent widths greater than around 1,000 or 1,500 angstrom or so. We're unable to reproduce the highest O3 plus H-beta equivalent widths, well over 3,000. This is an open problem. But at least the slightly less extreme EALGs we can actually predict. And so here what I'm showing you is on the x-axis is look back time, and on the y-axis is the ratio of the star formation rate divided by the star formation rate sort of at the current time. And the different colors show us the H-alpha equivalent widths going from around 0 to around 1,600 angstroms. So the galaxies with the lowest equivalent widths are the galaxies that are undergoing downturns in star formation, and the galaxies with the highest equivalent widths are the ones that have these extreme upturns. In fact, in order to get something around 1,600 angstroms, we need an increase in the star formation rate by a factor of 1,000 over the past 20 years or so, 20 million years. 20 years would be a bit too short. And that's really extreme. And it turns out that's not driven by mergers, it's just driven by turbulent gas physics in the interstellar medium. And if you go ahead and just stack the spectra of what these galaxies look like, the low equivalent with galaxies here, you see this, again, booming Balmer break, moving all the way up to the extreme emission line galaxies, booming carbon-4 emission, strong Balmer jump. In my last 5 minutes or so, I'm going to switch topics. Instead of talking about the interstellar medium, I'm going to talk a little bit about the circumgalactic medium in these simulations. So one of the unique things we do, very similar to the foggy simulations, hey Cassie, is we refine on the cooling length. So here's just an isolated disk galaxy simulation. On the left-hand side, you're seeing the standard run where your resolution elements are tracing mass. This is a very Lagrangian or quasi-Lagrangian formulation of the code. On the right-hand side, again, because it's an adaptive mesh refinement code, we can put our resolution elements anywhere we want. And the yellow is, again, oxygen 3, the purple is gas density, and the white is H beta. And what you can see is that the emission structures in the circumgalactic medium of this isolated galaxy, again, very simple toy model, are just significantly better resolved on the right than on the left. And what we can do is with Megatron, we pretty much can model any single ionization state that you want in non-equilibrium. So here's just hydrogen, here's molecular hydrogen. You see carbon-2 is well out in the circumgalactic medium, oxygen-1, oxygen-3, oxygen-6. There's carbon-4 right there, somewhere around here. We can do any of the individual iron states. So there's just a huge amount of wealth in these simulations. And one of the things I'm extremely excited by is that sort of at redshifts 3 to 4, what we tend to find with these simulations is if you put them edge on, so here's a disk galaxy, and you can see that it's an edge on disk. If you compare the photoionization rate coming from the radiation being emitted by inside this galaxy to the UV background, anywhere you see white, those two radiation fields are equal in terms of their H1 photoionization rate. The pink is dominated by the UV background, and the green is dominated by the local radiation field. You see this beautiful ionization cone structure such that above and below the disk, you're dominated by the local radiation field, but left and right of the disk, you're dominated by the UV background. And the reason why this is interesting, I think, is because the emission line luminosities have very different morphologies. So you can see H alpha is pretty much coming from everywhere, and I'll show you how much this depends on orientation. But for the most part, the CGM and emission, you can see the nitrogen-2 and the oxygen-3 are coming from this ionization cone. So they're excited by the local radiation field and not necessarily the UV background. So perhaps these certain ions, depending on the different ionization state you're looking at, you can find ways to constrain the local radiation versus the UV background. Again, orientation really matters. So here's this disk edge on. You see there's pretty much H alpha everywhere. But if you look at it face on, you see our beautiful H alpha disk. But now you're seeing the filaments. And again, this structure is really coming from the fact that we're refining on the cooling length. And what we're finding is that for some ions, we have really extreme non-equilibrium effects. In this case, you're just looking at the ratio of non-equilibrium carbon-2 to equilibrium carbon-2. In the ISM, you get some interesting effects at high density. I can discuss what those are if you're interested. But if you're looking more into the circumgalactic medium, you can see you can go above or below equilibrium by factors of 10. And this ion is particularly sensitive to these effects. And so, again, our photoionization models aren't really capturing this 100%. So just to conclude, the spectroscopic data from James Webb has revealed these numerous anomalies at high redshifts that we're currently struggling to explain, but I think that's extremely exciting because it opens up some physics that we haven't really thought about before. Ramsey's RTZ is this new code that we've developed, and the idea is to predict predict the spectra of galaxies directly from the simulations without post-processing. What we've learned from doing this is that inferring the physical properties from spectra requires extreme care, even for simple things like temperature and metallicity, but that's okay. I think we're in a much better position now than we were a couple years ago to actually do this. And finally, we have this new suite of simulations called Megatron, which is allowing us to make these one-to-one comparisons with observations at high redshift. We're quite a small team, so if you're interested, feel free to reach out. We're going to be making all the data public, ideally this summer. If we publish by this summer. It's going to be public this summer no matter what, whether we publish or not, so you're welcome to use it with or without us. So thank you very much.
Awesome. Questions?
So you mentioned the latest two papers that indicated two LRDs are potentially a black hole star, meaning you have a central black hole illuminate. First, my estimate or memory is that it was 10 to the 8 solar masses, not 10 to the 6, based on the global luminosity. But the question I had was that if you just surround it with a cloud of gas, it really depends as to what you're getting. It really depends on the dynamics of the gas, whether it's falling in, coming out, because it's similar to tidal disruption events where you destroy a star and you surround the black hole with a cloud of gas. And So is there similarity to TDEs, tidal destruction, or what did you do about the dynamics?
So we don't have too much understanding of the dynamics from the source. What I can talk about is the turbulence. So in order to get, I mean, as you know, the Balmer break is this actually sharp feature, and in order to make it smoothed out, you have to have some sort of kinematic motions, and you can do that with inflows, you can do that with outflows. But you need some sort of turbulence, and the amount of turbulence you need is approximately 400 to 500 kilometers per second, which represents a Mach number of about 100.
Well, it could be the inflow speed.
Could be the inflow speed too, and so I don't necessarily think it's an inflow, and the reason why I don't think it's an inflow is because in the high resolution spectra, the spectrum is around H beta is actually almost perfectly symmetric, which would be a little bit odd if it was a TDE or an inflow, because you would expect some sort of asymmetry, whereas if it's just turbulent motions in some very compact object, you could, hand waving and say that should be a little bit more symmetric.
So you think it's a photosphere, basically?
Well, again, these are very toy models. What I think is going on is you have some sort of very dense gas that has a very high covering fraction close to the black hole that's causing a Balmer break, and then you have some sort of like temperature inversion, almost like a chromosphere around our own sun, that's causing the H beta emission coming from outside this absorbing gas. But I don't want to call it a black hole star because I think people think quasi-star, and I don't necessarily think this gas is being held up by the accretion onto the black hole. It could be just an infalling cloud that, as you say, some got disrupted, and there's just a lot of gas and a high covering fraction. So
that's what these two papers called it a week ago.
Sure, sure. I'm very conservative with these sorts of things, but I think the analogy holds that it does look like a black hole with some sort of stellar atmosphere like thing going around that. Whether you call it a black hole star or not, I guess is up to you. But I would say the mass as the standard methods for computing the mass of these black holes do not apply to these objects. And so I don't think if you're using the standard luminosity line width relation that's been calibrated at low redshift, that's always going to overpredict. And there was another paper that came out that same day talking about how electron scattering can really cause the black hole masses to come down. If there's resonance scattering as well, the line width is not related to gravitational dynamics anymore. It's related to column density, and so I would be extremely hesitant by any black hole masses for these objects.
Do you make a prediction of helium too? So I would be interested to see whether it can be used in place of the O3 for the POP3 models.
Yeah, so we do make predictions for helium-2, but what we find is that the helium-2 equivalent widths can go from essentially 0 to 100 depending on the mass of the POP3 stars that we form in the simulation. So we stochastically sample an IMF, and so what that, we have no idea what the POP3 IMF is, and so we can discuss the uncertainties with that, and I think these are fair questions. If they were extremely massive, we get booming helium-2. If they were a lot less massive, we get much less helium-2. And so in our simulations, because our IMF goes from 10 solar masses to 1,000, we get all of the above. And so what I think you should take from that is if POP3 stars are massive, helium-2 is a constraint, although you have to be very careful because you can also get narrow helium-2 from Wolf-Rayet, especially at low metallicity. So I'm actually more interested in the 2-photon emission because I think that's a stronger constraint on the temperature of the stellar population.
Yeah, you think that?
Thank you, Harry. It's very leading the age. So the question is about the non-equilibrium emission line you produced on the fly. So how do you choose the time scale when you do this kind of non-equilibrium process production?
I mean, it's set by the ODE solver, right? So that, just so you know, the level populations are still in equilibrium, but the ionization states are in non-equilibrium. So we don't have enough memory on the computer to do the non-equilibrium level populations, otherwise we consider it. And so it's basically, we use the largest time step we can, such that we're using a semi-implicit method, which is quite different from what a lot of people use. So we have like a 10% rule, and we sub-cycle these time steps for every RT time step, which is sub-cycled on the hydro, which is sub-cycled on the gravity. So the time steps here can get to like seconds, or lower in the simulation. But it's dictated on the fly by the ODE solver.
Yeah, that's good.
The simulations where you were showing that sort of like pulsing ionization structure, is that pretty much just from like the pulse in the star formation rate, like starbursts?
That's it.
There's nothing else that could be leading to having different escape fractions of ionizing photons or anything like that?
No, so the production is of course dictated by, the production of the ionizing photons is dictated by the fluctuations in the star formation rate, of course. But not, just because you have a fluctuation in star formation rate doesn't mean the photons actually leak and get out. And so what we find, of course, in the simulations and have for many years is that you need temporally correlated supernova feedback to open up these holes to allow the radiation to go out. So what you see is if you plot F escape as a function of time, it's basically 0, and then even though the production rate is fluctuating up and down with the star formation rate, occasionally you get a burst of supernova feedback that's really clustered, that breaks a hole, and then all of a sudden it shoots up for a very short period of time to a high value and then comes straight back down.
Fantastic, thank you. So I wonder, when you say the direction methodicity is systematically overestimate, underestimate, I wonder if the electron density in different ionization potentials are accounted?
Yeah, so in general, like for normal ISM conditions, densities below around 500 or so, the direct method is always going to underestimate if there's temperature fluctuations present. If you go to high enough densities, again, just using 4363, not the aurora lines, you obviously collisionally de-excite the oxygen 2 lines, which again bring you down if you're using oxygen 2. I think that's okay though, because if you look at the metallicity measurements, they're mostly dictated by the oxygen 3 line and not the oxygen 2 line. That one gets collisionally de-excited at around 10 to the 4, 10 to the 5. And so at 10 to the 5, like for some objects, like you're probably familiar with Michael Topping's paper where they measure like an aurora line temperature of like 24,000 Kelvin. If you don't take the density effect into account there, you completely you underestimate your oxygen 3 5007 line, which causes you to overestimate temperature. And if you don't take the emissivity correction into account, you further underestimate it. So it all pushes you down. There's very few effects that push you up. So yeah, I think for certain objects, you need to be very careful about the densities that you're using for these emissivities.
Really nice talk. I was wondering, kind of about star formation histories. I think obviously you have the real one in the simulation. Kind of how, with the mocks that you can make, how accurate are the inferred star formation histories from observations, from the ISM at least, and then kind of a follow-on from that is when you move, can we use at low edge at least the ratio of certain lines in the CGM, because you've seen it's quite correlated to kind of look at the recent star formations.
So for the CGM, I haven't checked. I'll have to get back to you on that. I think for the star formation history, the exercise people have been doing is they've been taking the photometry and the spectra that we produce and then running them through like bagpipes and cross spectra and these other codes to see if they can recover what was in there. If you exclude dust, you can get the stellar masses and recent star formation history okay. I purposely left that to you to decide what okay means, because it's a hard problem, as you know. Once you include dust, and like if I go back here, this is the real problem. Like these blue lines all come from the same galaxy, and you can see that the magnitude, it changes by 1 magnitude. And so it's like, we see once you include dust, you get very different answers depending on the line of sight that you're looking at. And so these codes work extremely well in like the dust-free scenario, which means that like the low metallicity metal core stuff, I can, as long as there's no fundamental difference between the stellar populations in the real universe and what goes into our models, I'm willing to trust that the SED fitting codes are getting stellar masses and recent star formation histories okay, with that one very, very large caveat.
Yeah.
For the more massive systems, I think it's still a massive problem.
If you ask one quick follow, how expensive were these? Out of interest.
Like the whole program was about 60 million CPU hours. If AMD would allow us to put more RAM, like we're RAM limited right now, because we like, for like a typical Ramsey simulation, for example, we have like 10 hydrodynamic quantities. For us, we have like nearly 200. Yeah, so we're actually, coming back to this like stuff that Yifei was talking about, we can even do more physics because we're limited by the communication between the nodes. So give us better interconnect and more RAM, and that's what's going to drive our simulation time.
Okay, and we're perfectly on time. Let's thank Harley again. Yeah, if you want to meet with Harley, he has a couple of empty slots tomorrow, so feel free to. So,